Yes. Thank you so much. It was really wonderful session. جلستنا القادمة بإذن الله تعالى ستكون مع البروفيسورة شادية حبال، وهي التي تعمل لسنوات كاملة استعدادا لدقائق معدودة ليتزامن إطلاق ما تصبو إليه بشكل دائم ومستمر. دكتورة شادية حبال ولدت في حمص، ودرست الفيزياء والرياضيات في جامعة دمشق، ثم نالت الماجستير من الجامعة الأمريكية في بيروت، والدكتوراه من جامعة سنسناتي. عملت في مركز هارفارد وسميثينيان للفيزياء الفلكية في عام 1978 حتى عام 2000، وترأست فيه أبحاث الفيزياء الشمسية والأرضية، وهي اليوم أستاذة الفلك في معهد الفلك بجامعة هاواي. ومنذ عام 1995 تقود فريقا دوليا يعرف باسم شيرا الرياح الشمسية، والذي خاض أكثر من 12 بعثة كسوف كلي حول الأرض، من الهند إلى الصين إلى بولينيزيا الفرنسية إلى أستراليا. بيّنت أرصادها أن خطوط المجال المغناطيسي المفتوحة التي توجه الرياح الشمسية موجودة في أنحاء سطح الشمس كافة، وهو ما قلب نظريات راسخة متعددة. ولأبحاثها كذلك دور محوري في التمهيد لمسبار باركر الشمسي التابع لوكالة ناسا الفضائية. لذلك أول مركبة تدخل الغلاف الجوي للشمس كانت المسؤولة عن إطلاقها. نرحب جميعا بالأستاذة الدكتورة شادية حبال. الكلمة الآن متاحة. مرحبا بك دكتورة شادية، تفضلي.
مساء الخير للجميع. إذا ممكن ما تواخذوني، بس بفضل أعطي المحاضرة باللغة الإنجليزية. شكرا كثير على المقدمة. في تصليح صغير جدا، هو أنه أنا ولدت بالشام مو بحمص، والدي من حمص. هكذا.
بدنا نعدل فيها معدل المستوى.
نعم،
نعدل فيه فريق إعداد المحتوى. صرت قائد. تفضلي يا دكتورة.
Okay, شكرا. So the title of my talk is Chasing the Sun with Total Solar Eclipses from Damascus to NASA's Parker Solar Probe. And I wanted to add to it that this is a personal journey, my personal journey of exploration and discovery. So just briefly to recap on what the professor just said is, so I was born in Damascus, Syria, and then when I was little, my father went to England to complete his graduate studies. Sorry. And then we came back to Damascus. I got my undergraduate degrees in physics and mathematics from the University of Damascus. Then I went to the American University of Beirut and got a master's. And then I went to the University of Cincinnati in Ohio. Anyway, you can see from this map that I have traveled quite a bit across the world. And I'm currently now in Honolulu, which is an island in the middle of the Pacific. So this all started because as a child and a young adult, I was always very interested in physics and mathematics. And my idol at the time was Marie Curie. My dream was to do scientific research, but I never expected to end up doing research in solar physics or astrophysics. So I was really fortunate that my dream exceeded my accomplishments exceeded my expectations. So let me take you through this journey that's pretty unique in the sense that there are very few people who use the advent of total solar eclipses to explore some of the enigma or unknown about our space, our universe, and everything that surrounds us away from the Earth. This is one of the images that we took during the total solar eclipse of 2017, and it was processed by my colleague, Professor Drukmiller from Brno University in the Czech Republic. So all the images that I will show throughout this talk were actually processed by him, but the images were taken by different people in the group. So just briefly to tell you why this is such a unique advent to study the sun. And I often wondered, had it not been for total solar eclipses, many of our understandings of the sun, the solar system, and even beyond, all the stellar system might have been stifled just because of the lack of realizing that the sun doesn't stop, or what we see as the sun doesn't stop at the visible surface. It's not a solid surface, it's just a visible surface, but it extends far beyond. So it just so happens that perceive the diameter, the visual diameter of the moon and the sun as seen from Earth are very, very comparable. And when the moon passes it happens once every 12 to 18 months, when it passes between the sun and the Earth, then it can totally block the very bright disk of the sun. And then you can see the outer atmosphere of the sun, which is the solar corona. And the reason being, the corona is very, very faint. It's the brightness of the sun is 1,000,000 times brighter than the corona. That's why we can't see it. It's always there, but we just cannot see it except during a total solar eclipse. So the different phases you can start if you're lucky enough to be in the path of totality. And I should stress here from the previous one that the eclipse, the total solar eclipse, happens only over a swath on the Earth that's about 150 kilometers wide, but extends over about 3,000 kilometers. So you have to be exactly in this shadow band. So if it's a partial eclipse, you see the moon that's covering partially the sun, but it's really when the moon totally blocks the sun that you see this beautiful aura around the sun, which is called the corona, which means the crown of the sun. This is a video or an animation that was made for the 2017 eclipse, just to show you when it went across the US. So the black spot here is the moon as it's advancing with the sun across and you can see this is the shadow band. And as it's passing through different cities, these are the cities that will actually see a total solar eclipse. This picture was taken from our observations in Argentina in 2019. It's just how the sun appears in the sky when it's totally eclipsed. So you see this very bright corona. And you also can see here a very dark shadow band. So the sky turns into, the conditions are such that it's almost like nighttime, and you can see stars and you can see planets. So this was, of course, this phenomena is not new to us. Humanity has witnessed it over millennia. But what's interesting is that the Chinese were some of the first to make a record of a total solar eclipse on what they called oracle bones because they just etched them. But what's interesting and maybe relevant to us as Syrians or from the Middle East is that the oldest record of a verifiable solar eclipse was found on a clay tablet in Ugarit in Syria in 1200 BC. And this was confirmed. Yes.
Sorry for interrupting you, Professor. Are you sharing your screen? Anyone seeing the screen?
Oh, I am so sorry. You should have asked me earlier. I'm terribly sorry.
It's like figured out that like we are looking at something here.
I am so sorry. You should have told me earlier. Okay. Okay. Do you want me to go back? Can you see it?
Now we can see it. Yep. Thank you.
Okay, I'll just go back just just to show you what a total solar eclipse looks like in the
Fantastic. Yeah,
sky.
that would make sense.
Okay, I'm so sorry. Okay, so this is what you witness, and it's really a very it's like a primal experience, because all of a sudden the universe changes around us and the day turns into night and you see this glorious corona appearing. Okay, I won't waste too much time going back, but I will go forward. And this is where I was saying that historically the first verifiable solar eclipse was found on a clay tablet in Ugarit in Syria, and it was confirmed later on because the precise motions of everything in the universe, or the motions they follow, it's almost like clockwork. And we know exactly when an eclipse will happen and where it will happen. And there are documents covering about 6,000 years of eclipses, so they were able to verify this phenomena. And then this was a record of an Assyrian tablet from the 2nd century BC, where it showed that the Babylonians not only knew about the eclipse, but they knew how to predict eclipses, because there's a cycle of 18 years, and it's really due to the inclination of the plane of the orbit of the moon around the Earth and the Earth around the sun. So. Okay, so what did people actually see when the sun disappeared? So the first records were obviously by drawings, and of course more in the 19th century, people. So I have to tell you that the totality lasts anywhere from a few seconds to a maximum of 7 minutes. So you can imagine how difficult it was to make this record of what you would see and what you would draw. And often people had to complete the drawing after the eclipse from just visual memory. So these two were taken about 18 years apart. It's just what's remarkable is you see all these rays, these striations in spreading away from the sun. And then in addition, you see these pinkish protrusions that are different from the eye sees something that's more like what we call white light. It's just white. This particular example on the left was curious because it had something that instead of having rays going out, it also had this bubble shape. And I will get back to it later. Now, with the advent of photography, then people started to use photographic plates. And you can see that the records on the photographic records are very different from what people saw with their own eyes and what they drew. And the reason being that the eye has an incredible dynamic range, but with a camera, you have to take different exposure times so that you can follow the extent of the corona through space. And this is what we do. Now, the other thing that has been known for a while about the sun is that it has a cycle of what we call sunspots. So they are these dark blemishes that appear on the surface of the sun. And actually, Galileo used them to prove that the sun was actually rotating. But they vary as a function of time. And now we know that there is a cycle of about 11 to 12 years whereby the number of sunspots increases and decreases. So this plot here shows you the years, and here's the sunspot number. And you can see that there's a cyclical behavior. Not every maximum has the same number of sunspots. So the question is there any relationship between these sunspots on the sun and how the corona appears to the observer? So this was a compilation that was made by one of the people who worked with Maunder, and so he categorized them, the images or the drawings, as a function of their shapes varied as a function of time. So so now I'll move on to what are really sunspots and how do they impact, what is the relationship between sunspots and what we see, the rays that we see during total solar eclipses. So in 1905, George Ellery Hale discovered that the sunspots were using the Zeeman splitting effect, that these were actually concentrations of very, very strong magnetic fields on the surface of the sun. So this was really a major discovery that a star, such the sun is our closest star, is that magnetism plays an incredibly important role. And now we know that the magnetism is pervasive throughout the universe. Everything has a magnetic field, and it actually controls a lot of the gases in space, which we call plasmas, because they're mostly fully ionized. They're not like Earth, where they're neutral. And so going back then to the eclipse observations, it now makes sense to the connection between how the corona changes, and there is a direct relationship between the cycle, the magnetic cycle of the sun. So before we knew this, there was a solar cycle, but we didn't know that it was magnetically driven. Okay, so there was another very important discovery that was made during a total solar eclipse. Sorry, I'm not using this one. Okay. And that was in 1869, Young and Harkness used a spectrometer to look at the corona during an eclipse. So the red line, the red emission here was known as hydrogen from H alpha. There were a few other lines from hydrogen that were known, but this green line was, they couldn't associate the wavelength with any element that was known on Earth. And what was interesting is it took about 70 years before Adlin and Grotrian identified it. They called it coronium from corona. And they identified it as iron 14. 14 is the astronomer used the Roman numerals, but it's really iron that has been, ionized 13 times. For this to happen, that means the gas where it's emitting from has to be at 2 million degrees. Now, the surface of the sun is at 6,000. So all of a sudden, you have this very strange phenomena where you go from the surface of the sun at 6,000 to the corona at 2 million. So that was the first proof that the corona was actually much hotter than the surface of the sun, and that those temperatures, the gas couldn't stay neutral, but it had to be fully ionized. I need to just get a drop, some water, if you would excuse me for a second. Apologies, yeah. So following this discovery, Parker in 1958 showed that the corona couldn't remain bound to the sun by gravity, but it had to expand, and it expanded supersonically, meaning that it started to accelerate as it expanded away from the sun. And he called this expansion the solar wind. So the solar wind is now was confirmed in 63. Both Americans and the Soviet Union started to launch satellites into space, and it was the American satellite that detected the solar wind away once it went outside the magnetic environment of the Earth and around the orbit of Mercury. So so if you think about it, these discoveries were really seminal in opening up the space age of discovery, because then at these temperatures, it was clear that one could observe the corona in X-rays, in ultraviolet, without having to rely on total solar eclipses. But in the remaining of this talk, I will try to show you how these are not sufficient, and that total solar eclipses are really critical for understanding or identifying the sources of the solar wind and what really defines the different characteristics of the solar wind. Sorry. Okay. This is just an artistic rendition of the outflow of particles from the sun. This was the plot from this very important detection of the solar wind in interplanetary space. So the speed of the wind varied between 300 and 800 kilometers per second, and it had some kind of cyclical variation. And the speed, unfortunately, here one of the curves is the velocity as a function of time. So this is the velocity, and this is as a function of time. The observations were taken between August and December, about 3 to 4 months, and they recorded these continuous flow of particles past the spacecraft. And what's interesting is the characteristics of the solar wind have not changed since then. This was in 1963. And we still observe the speed, which is between these two extremes. Now, evidences for the solar wind is found in the ionized tails of comets. Comets have two tails. One is a dust tail and one is the ionized tail. And the ionized tail is always pointing anti-radially away from the sun in anti-sunward direction. The aurorae are another manifestations of the solar wind, because you have, now we understand how it happens. Basically, the solar wind particles can penetrate the Earth's upper atmosphere, not directly to the Earth, through the special configurations of the magnetic field of the Earth, and they usually happen in the north and south poles. And you see these gorgeous sheets of ionized oxygen and nitrogen. So all these are a consequence of the solar wind interacting with the ions in the ionosphere. Now, what I'd like to next go into, what are the scientific contributions of the solar eclipse observations in the age of space exploration? Because people often say, well, we have all these satellites in space. Why do you keep on doing eclipse observations? The main problem is summarized here. You see, in the extreme ultraviolet, the emission that you see cuts off very, very quickly. So here is the sun is underneath this inner circle here. And then, Leo in the early 30s, 1930s, came up with a optical design to make to produce something like a artificial eclipse. So it's basically an occulter that you put in the path of your optics, and you create an eclipse. That's used very frequent in space. But you can see, so what you see in space is this outer emission here. But the problem is that you have this gap. So the occulter has to extend past the surface of the sun, because you get the diffractions at the edges. And then you have a missing space, and that missing space can only be covered by total solar eclipses. So you really can't tell just from this where whatever starts at the sun, how does it end up connecting to what you see further away from the sun. This example is one of the inner picture is from the extreme ultraviolet taken from space, and the blue is our eclipse observation taken at the same time. So you can see that the continuity between these very, very fine details from the extreme ultraviolet into the fine details of the corona seen in the eclipse image are pretty much astounding, and it just shows the value of these eclipse observations. So what do we know about magnetism? So I wanted to share with you this video, because it tells something about, it's not just that you have an eclipse or the corona changes as a function of time, but it shows you really that the magnetism associated with the sun actually produces a very, very dynamic outflow. Now, in this picture, the image were taken by the extreme ultraviolet, one of the telescopes in space, observing the sun continuously. The solar north is to the left, and it's just because I wanted to show you to focus on this region here, where you have these very fine arches, and you have these filamentary features. These are observed in the extreme ultraviolet, and then the eclipse observes further away. But with the eclipse, we can't see what's happening on the surface of the sun. So what I'd like you to focus on is this region here. The progression is very slow, but you're going to see something happening very suddenly here. So you have something almost like a fire, and you have this burst of explosion, And all this is magnetically driven. And then you have these neutral particles that fall back into the sun and produce these secondary flares or fires. Okay, so going back, this explosion is now known as a coronal mass ejection. And going back to that picture by Temple, the drawing, what he saw this explosion, which we call coronal mass ejection. He saw it in the eclipse image, and this is what he drew. So this is another just comparison. I wanted to show you that when you occult the sun, and you see this huge bubble expanding beyond the occulter, but you don't know where it starts from. Whereas in this example, which was taken in 2013, this is the eclipse image on the left, and this is what was observed from space. And so in the eclipse image, we captured this huge bubble over here and its core, and I'll show you how it appeared in exactly behind. So you missed from space, you can see this, well, you'll see this bubble appearing from behind the occulter. It's here. And this is exactly this one. I'll just stop it. But you can't tell how it was attached to the sun. And this is extremely important because for a long, long time, people thought that this bubble just kind of detaches from the sun and just goes into interplanetary space. But the eclipse images shows you that it stays attached to the sun. So it expands, but it's still anchored at the sun. Okay, so now moving on to this, I gave you a little bit of a taste of what what the science is. Here, I want to just focus a little bit on the expeditions that I led. So this year was my 21st expedition, and we just came back from Spain. So these are the different. So the totalities occur because of the path of the moon and the plane of the inclination path of the moon and the Earth's orbit around the sun. Eclipses can happen anywhere on Earth. And sometimes they're very remote places, like here in Antarctica, that was the most remote. Here we went to Svalbard, north of Norway, and in Tatakoto. So you have to prepare for all these different places. So it's quite an involved preparations. It's almost like field work, but for astronomy. I mean, geologists and archaeologists do that all the time, but for astronomers, they don't. They just go to the telescopes, whereas we carry all our equipment to the different regions across the world. And the name of Solar Wind Sherpas came about in 97. After the eclipse, one of my friends, colleagues said, well, we have to give a name to our team. So I came up with the name, the Solar Wind Sherpas, meaning we carried all our equipment. And we used to carry a lot in backpacks. Now we try to ship a little more than before. Now, unfortunately, clouds are, for all of astronomical observations, clouds are a threat, of course, clouds or rain or whatever. And when I calculated once how many I lost due to clouds, it was 40%, so which was a staggering number given all the preparations and the cost and so on. So these are the tools of the trade. So what we have is spectrometers, and everything has to be compact because obviously we can't carry very heavy equipment. And these are special telescopes. So you have a camera at the back, the lens, and we have special filters at the front to be able to extract or see these different colors in the corona, like the one I told you, the coronium, which was discovered in '69. So from these different observations, we can tell not only we can probe actually the temperature in the corona. So it's almost like putting a thermometer in the corona and figuring out how the temperature is distributed in the corona. And then you have the white light, which have these incredible details, which is everything. They're produced by free electrons streaming away from the sun and reflecting the sunlight, which is why we see them. And because everything the sun is a magnetic object, you have magnetic field lines streaming away from the sun, but you don't see magnetic field lines. You only see them through the motion of the electrons that spiral along the magnetic field lines and trace actually where the field lines are. So these are just examples of the volume of equipment we carry to different places, and we take, boats, airplanes, whatever. Oh, sorry. This was in 2017. It was one of the largest groups. We had 5 observing sites across the US. And this one was in Antarctica in 21. This was the furthest, most south eclipse. We were on a ship because there was no way to access the land. And this was as we were approaching the Antarctic Peninsula. The day before the eclipse was pretty clear. And fortunately, the day of the eclipse, it was all gray. So one of my teammates says, why don't we fly a kite? So in 23, we did fly a kite, and this was a 6.5 meter wide kite. The payload was a 12 kilogram spectrometer. And this is just for the fun of it. I want to show you. This was actually the day of the eclipse when we launched the kite. So the kite is up here, and then the spectrometer was attached at the... You can hear the wind. This was in northwestern tip of Australia. And it wasn't a perfect experiment, but we got spectra of the corona during totality. And it was quite a thrilling experiment. Okay, so 2024 was the most ambitious eclipse expedition that I led, because we had 3 observing sites on the ground. It also went through the US from the southwest to the northeast. I had enough money just to go past Arkansas, starting from Mexico. But we also wanted to fly the kite, and we also got money from NASA to fly our equipment on board on the wings and the nose cone of an airplane. That's their airplane. So the spectrometer was here, and we had the spear pods hanging on. So we had the imagers on the side. This was a very challenging experiment because the wings had significant vibrations which we weren't aware of. So we got the images, but they were not centered, and it was very difficult to recenter everything. This was in preparation for the flight. This is from the ground. Mexico had terrible weather. You can see here they had almost like a sandstorm, but they managed. The wind was very fierce. They were holding on to the observing tent. This was in Kerrville, Texas. They also were clouded out, so you see they could barely see the corona. But fortunately, in Kerrville, in Arkansas, we had perfect weather. And this gives you an idea of the size of the latest size of our equipment. Okay, so I told you the importance of these observations is really to figure out something about the origin of the solar wind, the properties of the solar wind. And I mentioned these filters that we use. So they're tailored. It just so happens that iron is the most dominant element in the corona, and it appears at different ionization states. So iron 14, this one is the coronium, but subsequently people discovered several emission lines from iron. And there's the iron 10, 11, which we imaged for the first time in 2006 during the eclipse in Libya, and then iron 13, which was known before that. So I'm plotting here the ionic abundance versus electron temperature, just to give you a feel for why it's important to observe in these different lines, because each one of them corresponds to different temperature, electron temperature in the corona. So if you see, for example, emission in this green line here, and what I called iron 10 plus, which corresponds to a temperature of 1.2 million, but you don't see it in iron 13 plus, you know that the plasma that you're observing is at this temperature. Whereas, and vice versa, if you see something in iron 13 plus and don't see it in iron 10 plus, then you know that it's that temperature. So by observing in these different emission lines, we can map the electron temperature in the corona. So these are the instruments we use for that purpose. This is an example from the 2023 eclipse. So the top two are from what we call the white light. So these are just all the electrons streaming away from the sun. And all the structures you see are actually the magnetic field lines that are emerging from the sun and escaping into the interplanetary space. And this is basically, they are the solar wind. So the solar wind is traced by these magnetic field lines. Now, the bottom ones are images that were taken through these different filters. And if I didn't tell you, for example, if you look at the middle one and the one to the right, if I didn't tell you this was the same eclipse, you wouldn't have necessarily thought it was. But you can see how different the two are, meaning that the temperature across the corona is not uniform. Here, these are all the features or the magnetic structures that are at 1.2 million degrees, and these are the structures at 1.8 million degrees. So from the two, we combine the two and we make this color composite, which tells us, which is basically the map of the temperature in the corona. So you have intermediate temperatures when the two kind of have some overlap. The most important thing to take away is that everything that looks like it's streaming away from the sun is at the cooler temperature, and the rest, which are arches, which seem to be anchored at the sun, and we call them streamers, they're all at the much hotter temperature. And in addition, you have these pinkish emission, which I showed you in the first drawn images, which we call prominences. Now, they're very special in the sense that, if you recall, I told you that we're talking about temperatures of 1,000,000 degrees in the corona, whereas these structures are 100 times denser, but also almost 100 times cooler. So it's very surprising because you say, well, it's almost like you're putting an ice cube in an oven, and the ice cube stays an ice cube. It doesn't change. So this is what's one of the puzzles of these prominences. And I'll show you in what follows that they are actually responsible for all these dynamic events in the corona. This is a comparison between observations taken in 2017, which was at the declining phase of solar activity. The top one here, so it's iron 1014 and the color composite, and this is the white light. And the bottom one was from 2024. So you can see that the corona looks very, very different, but regardless of how it differs, everything that's streaming away from the sun without any interruption, basically these continuous rays are at the cooler temperature, but everything that stays kind of attached to the sun and it's more confined is at the much hotter temperature. So all these are clues for scientists, I started myself doing this also, is that what is causing this temperature to rise suddenly, and also what is causing this distribution not to be uniform. I mean, there's something going on in the corona where some places are hotter than others. So this is an ongoing research direction that everybody, lots of solar physicists are pursuing to try to understand why the corona is behaving this way, because it has implications on the solar wind, which as it traverses the interplanetary space, it goes past all planets and impacts their magnetic environments. And if they don't have a magnetic field, then it impacts their atmospheres directly. Now, there's the other aspect of the corona, which we were able to explore from total solar eclipses, is this dynamic corona, or what I call the turbulent corona. So again, this was associated with the CMEs, which I showed you earlier. And if you look at, this is a close-up from 2024. Now, if you go look at this larger field of view, you see all these rays going around from the sun. But if you look very close in, you see this very, very complex structures. It's looks like a turbulent medium. You have, I'll show you examples of waves, of vortices, of what we call plasma instabilities expanding, starting in the corona and expanding away. So the big question is, what is their role in one is, how do they originate at the sun? And second, how do they impact the solar wind? And what is their role in how they impact the planets? and Earth. For us, Earth is the most important one. So here I just have a few examples. Here there was in 2020, there was a huge CME here. There was a ripple around the CME. So these, what I'm showing you here are details that we cannot get from any space instrument. So all these details are only available, or we managed to get them from these total solar eclipse observations. Now, going to Parker Solar Probe, which was mentioned in my title, I did work for almost 15 years on the concept of the Parker Solar Probe. I was involved in the different scientific committees and so on. But at the end, I was not involved in any particular instrumentation. But what's interesting is now the probe has been launched, and it's well, the idea is it's orbiting the sun and it's already gotten as close as possible to about 10 radii away from the sun. And because the sun is so bright, they cannot have an imager that looks directly at the sun, which is really kind of such a shame, because you're so close yet you cannot look at the sun. So they look to the side in white light. And what they have seen, they see some, features streaming away from the sun, and you see these little bubbles going, and then you have this huge coronal mass ejection. So this is looking to the side, but they cannot see the origin at the sun. So what we did is we compared our eclipse observations with some of the findings from the Parker Solar Probe, just to show that what they observe is not created in situ, meaning in space, but it actually originates at the sun and propagates away from the sun. So these are some examples. So on the left here, you have some examples from the eclipse images. We have what we call vortex rings here, and then this is what you see in the Parker Solar Probe. You see exactly the same thing, but further away from the sun. This is their animations, but I don't know if I have enough time. Okay. So here it's just, these are still, of course, the eclipse observations, we don't have animations because it's a very short period of time. But we're comparing them, I'm just comparing with what happens, and what is seen is in interplanetary space. This is another example of what we call a Kelvin-Helmholtz instability. You can, some examples exist when some cloud formations, you can see these clouds forming like ripples, which is, they form in all kinds of fluid media and gaseous media. And here they're actually forming, this was probably the largest, the most spectacular Kelvin-Helmholtz instability recorded in the corona. And these are the comparable ones, which are really tiny in the Parker Solar Probe. So they have not observed anything close to what we have been able to capture. And finally, you see these coronal mass ejections. They have different types they see, but we also see different types. So I have put some examples here on the left from the eclipse images at the sun and what they observe in interplanetary space. So their interpretation that there is an evolution and they show up in different ways is not correct, because we show that they happen at the sun, and it depends on your viewing angle. It's still this very, very complex filamentary bubble or closed structure, but it depends on how you see it from which angle ends up appearing in space. Okay, and so now the question is, where are these huge explosions starting from? So I go back to this picture. If you remember, I showed you this movie. So it's really the prominences. And what's interesting is they occupy a very, very small volume in the corona. And it's literally like what people say, the tail wagging the dog. So they're very, if you recall, I said they're very dense and very cool, but sometimes part of them gets ionized by the hot material surrounding them, and you can see the connectivity. So it's an interface that is thermally unstable. So you're going from something very cold and dense to something that's very tenuous and hot. So obviously that interface is not going to stay stable. and you have continuous dynamic movements inside the prominences. And here, this was an example from a part of an eclipse image from 2008, which is probably one of our best examples. You see this prominence protruding in the corona, and it's surrounded, the green, remember, is iron 14. It's surrounded by the hottest material there. So it's invariably, we invariably find that the coolest object is surrounded by the hottest object. So clearly the two are not compatible. And this is what causes these dynamic events and what causes this these explosions. So I'm going to end by just my message is the next time you look at the sun, try to imagine its hidden beauty. The next, this year, as I said a few weeks ago, the eclipse was over Spain, so we were there and we were very successful in our observations. Next year, the path of totality is going to cross all of North Africa, the tip of Spain, and it goes over Luxor and it goes over Jeddah. Now, the best places, you also have to take into consideration the weather pattern and the atmospheric conditions. So Luxor is very tempting. It's going to be mobbed by people. So we will try to avoid it because we cannot operate if there are too many people around us. And then in 2028, the path of totality goes across Australia. Now, this is an unusual sequence because usually they come at more than 12 months apart. This is a sequence of 3 at less than 12 months apart. So it just makes our lives ever more challenging and maybe exciting. Now, I'd like to end by saying that I wouldn't have been able to achieve this science without having an incredible team of Solar Wind Sherpas. And I'd like to acknowledge support from NSF and NASA. Thank you.
Thank you. Thank you very much, Professor, for the fascinating talk. A lot of things to think about.
Yes.
You've just showed us actually how much can still be learned by observing a phenomenon that has existed for centuries. So thank you very much for that.
Millennia more like.
Indeed.
Yes.
I have a quick question here. After leading so many expeditions to tracking the eclipse, what have these experiences taught you about making good scientific decisions when you have only few minutes to observe something you may have prepared for years?
Okay, so it is actually a challenging endeavor. We work extremely hard. So after each eclipse, I should say that what's rewarding and actually astounding is that every single eclipse image is different from the next one. Even though there's a cycle effect, they more or less, there's some kind of overall aspect to the corona. But each corona is different, and each one teaches us new things. And with also the beauty of doing things from the ground is once you launch an instrument in space, you can't retrieve it to take advantage of the advancements in technology. Whereas we do, and for example, for us, the most important part are the cameras or the detectors and the filters. So with the improvement in technology, we take advantage of the cameras, which have gone down by a factor of 10 in cost. So we're able to explore more emission lines. And so after each eclipse, we try to analyze the data. Now, grant you, the team is very large from an operational point of view, but the actual people who do the analysis of the data is rather limited. So we're a little bit stuck. Sometimes we run behind because we don't have enough, it's myself and a few scientists and graduate students. So we have to analyze the data as fast as we can, and then obviously you publish. But many times, especially this next sequence of 3, it's going to be very challenging to keep up with everything. So from what we learn from each time, we try to adjust and try to think of adjustments to the instrumentation or to the way we observe, our observing strategy. Also selecting the observing sites is also very demanding because there are so many different factors. Accessibility is the most important one. So there are all these factors that one has to take into account. And we're just a very small team. I mean, for anything from space, you have teams of hundreds of people. We're just a handful of people organizing everything. Does this answer your question?
Yep, indeed. Yep. Thank you. Othman, I see your hand.
Yes, thank you, Prof. Shadéة, to come and join us at this very insightful presentation. I think you were born in Homs. I was born there too, so I feel very connected.
I was not born in Homs. I was born in Damascus.
Okay, close to there, inshallah. I think
My father is from Homs, but I was
my father was born there. Yes.
Mm.
So in relevance to what we are doing today as we are promoting this to Syrian students, if you were a young Shadéة Habbal studying physics now at Damascus University today, and under the circumstances Syrian students face now, which are many challenges, many were exposed today during the beginning of the conference, what opportunities, if you were that student, would you want the university and the Syrian scientific diaspora to create for you?
Okay, I wanted to talk about this, but okay, so I'm glad you asked the question. I think, well, first to succeed, I mean, you start with a dream and you want to do something. You have to believe in yourself and you have to persevere. I know it's very, very difficult, especially under the current circumstances. It's extremely challenging. But there are opportunities in the following sense. For example, in solar physics and in astronomy in general, there are lots of data. There are plenty of data available to the public, which can be accessed by anybody in the world. And an example, for example, now we receive lots of, as an editor for one of the astrophysical journals, we receive a tremendous amount of publications from China who are taking advantage of the proliferation of space-based data. This is something, of course, students in Syria can take advantage of. But you can't, it's not enough to have access to data. You need some ideas, you need a scientific goal, and you need somebody to lead you. So if we can come up, for example, with a list of people like myself in abroad, outside, who are can come up with ideas and kind of serve as advisors, or I don't like the word mentor because mentor is not necessarily just an advisor. So who can come up with ideas and just steer the students, just like we advise our graduate students. We could try to do something with students from Syria. It won't be, I mean, I don't have to be the person. I'm saying there are lots of people they don't have to be of Syrian descent. They can be any nationality who would be very interested in working with students who are who have the drive to do something, to explore, and so on. So we're not short of ideas. We're short of human power. And if that human power exists in Syria, then I think we should take advantage of it. The most important thing is obviously to have the background in for my field. You have to know something about physics, of course, mathematics. Some programming skills are always useful, and I think lots of students these days have acquired programming skills, and understanding of spectroscopy. So it's basic physics. I mean, there's nothing We don't use sophisticated math. We don't use sophisticated physics. It's all based on very, very basic physical principles in what we're doing in solar physics. So I would say this would be the one way forward, because short of somebody, of course, if you leave your country, go abroad, that's different. But if you are in Syria, you have no way of leaving or experiencing research outside of Syria. I would say that would be the opportunity to take advantage of the fact that the data exist. You need some ideas, you need somebody to steer you, and the student has to have the drive to pursue the research.
Yes. Great, thank you.
Any other questions? غدار تفضل.
It's Ghadir, sir. Dr. Ayhan.
Sorry. Yeah, sorry.
No problem. It's confusing in English. Thanks for you, and thanks for Professor Shadia for this great amount of information and showing basically for someone like me who have this ambitious in studying physics and astronauts, it's amazing to show this from an expert point. So I'm gonna ask you from an expert point also. In today's world, where we having now this major revolution of AI going or involved in many specters and measures, if that makes your job easier using this software or using this model to analyze data or to predict some actions or to understand some issues that happening in front of your eyes, maybe no offense, but maybe it's make it easier or it's make it accessible more to understand those principles or things?
Personally, because the data that we collect from eclipses is rather limited compared to what you have from space, which is pouring in continuously. So there are certain research projects which can take advantage of AI. The eclipse is not one of them, because for AI you need to train the software on large data sets, and it's happening in different fields, and astronomy is one of them. But so far it hasn't shown great success or great promise, but I know that it's many people are pursuing that venue. So as far as research, you have to think about it, I think, from the AI point of view, it's like a statistical study. So anything where you have large numbers, AI can be very useful. But when you have much fewer databases, it doesn't make sense. It doesn't help us. Maybe it makes sense, but it doesn't help. It doesn't help. I think we have to get to the point where it's still an observational field. For example, lots of the features we see in the eclipse images, it's by detecting by eye. You cannot train, because if you want to train a system, you have to know what you're training them to see. But we are discovering new things every day. So how can you train some system for something that you yourself don't know? So I don't think it will work. And the visual discoveries have been extremely important. So the visual discoveries lead us to the scientific questions and then to the mathematical and physical explorations.
Thank you. Thank you again for your awesome and inspiring lecture. The many questions that are left with us to think about and to be inspired with. Back to you, Othman. Maybe we have now 2 workshops parallel running or so. I don't know.
Yes, just a busy day. Again, Professor Shadية, shukran كثير. You were one of the ones to motivate us to run this conference. When we did first reach out to you, you showed big support, and you agreed actually to join us among other keynotes, which really pushed us to deliver this workshop today. We had roughly 97 participants today. Maybe the number dropped, which is ordinary, about 45 now. And again, hopefully through social media, we're going to reach to hundreds more. I hope it will be a successful journey, and this is the first round of the conference. So thank you again. I really appreciate it. شكرا كثير دكتور شادية على يعني دعمك لنا بحضورك وموافقتك تكوني معنا.
بتكرموا. أنا كتير يعني شاكر تكون كمان إنك دعيتني، لأنه بالنسبة لي هالشيء مهم جدا.
شكرا يا دكتورة. شكرا.
شكرا. هلين.
Okay. MashaAllah, this conference is